section, we're talking about alternating series. The goal is to determine if an alternating series converges. So what the heck do I mean by an alternating series? Well, it's alternating in sign from positive to negative or vice versa. So here's the definition we'll take. An alternating series has the form, okay, we're going to take the sum from, say, n equals 1 to infinity. We'll make it alternate by taking -1 to the n minus 1 power, but I mean, it could be -1 to the n power or -1 to the n plus 1 power, as long as it alternates every term, the sign from negative to positive or vice versa. Times, we need something else in there, otherwise it would be really boring, times some nth term formula of a sequence Bn. So you're used to calling the guy after the sigma notation an. So the an in this would be the whole thing. The an would be -1 to the n minus 1 times Bn in the lingo that we've developed in previous sections. So that's an alternating series where we insist that Bn is greater than 0. Otherwise, if that went negative, it could mess up the alternating nature of the series. Turns out, it's pretty darn easy to figure out whether an alternating series converges. So this is called the alternating series test, AST for short. If the alternating series, the sum from n equals 1 to infinity, -1 to the n minus 1 times b sub n greater than 0, satisfies two things, then the series is convergent. Okay, so we're going to fill in the blanks here. What two things does the series need to satisfy? Well, first of all, the b sub n part has to be decreasing. b1 is going to be greater than or equal to b2, which is going to be greater than or equal to b3, which is going to be greater than or equal to b4. Okay, I could do that the rest of my life, so I'll just put a ... The sequence bn decreases as you plug in bigger and bigger values for n. In general, you could write that like this. You could write it like bn plus 1. I'm turning things around now. So bn plus 1 would be less than or equal to the term that comes before it, bn. That's another way to write it. So it's a decreasing sequence, bn is. And then what does it have to decrease to? It has to decrease to 0. So the limit as n goes to infinity of bn is equal to 0. So if you wanted to express conditions 1 and 2 as one condition, it would be that bn decreases to 0. And it doesn't, after you get past a certain value, perhaps it doesn't oscillate. So if it didn't decrease from b1 to b2, fine. But eventually, you'd want it to start decreasing. Okay. So then, if those two conditions are satisfied, then the alternating series converges. That's the alternating series test. It's one of the easier tests, actually, to use. Could we prove it? Let's try to use a pictorial depiction of a proof. Of course, you can't prove anything using a picture, but this is about as close as you get. Down here, I have a number line, and here's 0. Let me set up kind of a vertical bar, a couple of vertical bars here. Let's say the distance between these two bars represents b1. So this distance from, say, here to here represents the first term in the sequence given by the nth term formula. Oh man, it's been a long weekend. Bn. So okay, so well, you're familiar with that. We can let length represent a number, right? A positive number, sure. And we know b1 would be positive. So b1 would be s1, the first partial sum. What do we know about b2 lengthwise? It should be less than that, yeah. And if b1 is, say, positive, then the next term in the actual series would actually be negative b2. You see what I'm saying? The first term would be plus b1. The next term in the series would be minus b2. So that minus b2 lengthwise would take us back the other way, but not as far, maybe to here. So that would represent, that length would represent the second term in the series. Because remember what this series represents. It's the symbolism represents b1 minus b2 plus b3 minus b4. So, and then plus dot dot dot. So I'm drawing kind of a pictorial representation of that. So pictorially, those are the first two terms actually. So you end up here after the first two terms. To get the next partial sum, add in plus a b3, but we know that b3, absolute value-wise, b3 is less than negative absolute value of negative b2, or just b3 is less than b2. So you would end up perhaps here. You guys see what I'm doing? We go back another time. Oh yeah, you add in the next term, but the next term is a negative b4. b4 is less than b3, so maybe you end up here. And then, well, okay, this is not exciting, so you're going to be going back and forth and back and forth and back and forth. And eventually the idea is you're going to end up at some s because of the alternating nature of the series and the fact that each successive bn is less than the previous one. The value of the partial sums are converging to s. They're getting closer to s. Okay. I always like that picture. So then let's apply the test. Does it converge? Part A, we have the sum from n equals 2 to infinity of negative 1 to the n, and then the natural log of n on the bottom. So negative 1 to the n divided by ln of n. Okay, what do we start at in this one? N equals 2. Why? What's the ln of 1? 0. You don't want to divide by 0. So is it written in stone? The starting value of the series, is that written in stone? It's not. And usually when we express the theorem or a generic series, we start it at 1, but we don't have to. That's just so we can write something down. Okay. Well, can you identify the Bn? Yeah, Bn is just what you get, what's left when you take out the factor of negative 1 to whatever power. Notice the negative 1 isn't to the n minus 1 in this case. Doesn't matter. That's Bn. Two conditions. It has to decrease, and it has to decrease to 0. The limit, in other words, has to be 0 as n goes to infinity. That's for Bn, not for the series, but for Bn. Don't confuse the sequence Bn with the series, right? So is it clear that Bn number 1 decreases? Yeah, because ln is an increasing function. As n increases, ln increases, but it's in the denominator, isn't it? So I think it's pretty clear if you just go like this. Well, okay, b2 is the first term, so that's what you'd want to write down first. 1 over natural log of 2 is certainly less than 1 over, what's the next term in the sequence given by Bn? 1 over ln of 3. What's the next term? And I made a mistake here. I need these guys going the other way. That would be helpful. So this guy is bigger than this guy, which is bigger than this guy, which is bigger than this guy. And so what allows me to say this? The denominator is increasing as n increases. So the numerator stays 1, so the overall value decreases, right? It's a known fact. Do we need to say much more than this? kind of checking a box here, aren't we? So it decreases, big old check. So going back, decreases. This is kind of what we showed, right? All right. In this case, it's strictly decreasing. And then what about the limit as n goes to infinity of 1 over natural log of n? Is it clear that since the denominator just goes to infinity as n goes to infinity, and numerator stays the same, do we have to write anything down here other than equals 0? No. So when you know the denominator of a fraction increases to infinity as n goes to infinity and the numerator stays the same, there's no work that you need to show. We know then that the limit is 1 over infinity. To kind of abuse the notation, you can't really say 1 over infinity, but we kind of think of it that way. And then we think of 1 over infinity as being 0. So what's your conclusion? So the series does what? The series converges by, let's use alternating series test, the abbreviation AST. You know, it was so obvious, and I didn't mention it, but maybe we should get in the habit of mentioning it. Bn must be greater than 0 for this to work, right? It's pretty obvious that for n greater than or equal to 2, the natural log of n is going to be greater than 0, which means 1 over the natural log of n is going to be greater than 0. I didn't mention it, but it wouldn't be a bad idea to get in the habit of mentioning that. Hey, that's not so bad, right? It's better than the integral test. So that's it. That's the test. I mean, yeah, it gets a little more difficult when we're not sure if it decreases, and I'll show you that, but that's the test.